This is note card 1 from Stacy McMullen. She calls this average and instantaneous speed. So before we actually jump into the first note card here, let me tell you about speed real quick. Speed is always equal to the absolute value of velocity. Okay, this V here stands for velocity. So let's think about that real quick before we jump in. So I'm just going to use a spare sheet of paper. Okay, so let's just kind of review absolute value real quick. So if I just said, what's the absolute value of 5, you would say, well, it's 5. But if I say, what's the absolute value of -5, you would say that's +5. Okay, now let's put that in the context of a speed graph. So we think about speed, think about when you're traveling in a car. When we're in a car, we measure speed by a speedometer. Okay? And what we notice in our car, it's always positive. So speed is always positive. That's different than velocity. Velocity can either be positive or it can be negative. Speed is what's called a scalar quantity, but velocity is a vector. Now, if velocity is positive, we're usually talking about particle motion, so that's when a particle travels right, if we're moving right to left, or up. But if velocity is negative, we're traveling left or down, if a particle is moving up and down the y-axis. Okay. So if a particle has a negative velocity, let's say it was -10 meters per second, well, its speed would actually be, so if the velocity equaled -10, okay, the speed would just be 10. Okay, so that particle is still moving 10 meters per second, it's just moving in a negative direction. So that's what the negative there tells you. This negative tells you about direction when you're talking about velocity. Okay, that's why it's a vector. It has magnitude and direction. It tells us about magnitude and direction. Whereas speed, the scalar quantity, just gives us the magnitude. All right. So for example, if I had a velocity time graph, all right, on that axis, if I put the velocity, and here I put the time, okay, let's just kind of do one of these. Okay, so say that was the velocity time graph. Well, if we did the same graph here, but we called it a speed time graph, all right, here over this portion of the graph, the velocity is already positive because it's above the x-axis or the time axis. So that part stays the same over here. But speed can't ever be negative. So this part right here that was underneath, okay, think about all those y values, all those velocity values, they're all here. They're on the negative part of the y-axis. What it actually does here is it flips it over to the other side. So this triangle that's beneath the x-axis or beneath the time axis would move above the x-axis on a speed graph. All right, now over this next part, this next triangle, it's already above the x-axis, so on a speed graph, it would stay above the x-axis. And this last part is underneath. All right, if you turn it into a speed graph, then this part would move above. It would be its mirror image. Okay, so that's the differences between velocity and speed. So I just wanted to illustrate that. Now let's actually get into the note card. Now we're talking about a specific type of speed, okay, which she's calling average speed. All right, so to find average speed, okay, what we're going to do, how we find average speed is we take the total distance, actually we take the absolute value of total distance, okay, and we divide it by time. So if distance, for instance, if distance is in terms of miles and time is in terms of hours, our average speed would be measured in miles per hour. That's what we would do. All right. And on a graph, it's the slope of the secant line of the position function. All right. Now, instantaneous speed, it says, is the speed at a specific instant at time. So you look down when you're driving, at a certain instant of time, you might be going 63 miles per hour at that certain instance. Okay, but maybe over the first 5 hours you're traveling on a long road trip, you might not be going 63 the whole time. Okay, maybe 1 hour you ran into a traffic jam and you were going very slowly, and then it opened up and you stepped on the accelerator and you moved a little quicker. Okay, so that would be instantaneous speed. Okay, it's at one moment of time, but over a long period of time, you can average out a different number. Okay, now on a graph, it's the slope of the tangent line, and we'll get into that. It says analytically, we need calculus to determine this instantaneous speed. So what is this whole average versus instantaneous speed, or slope of secant line, slope of tangent line? Let me kind of go back down to another graph. So let's say we have some position function. Okay, so we'll call this a position function. And this is time. Okay, so let me just kind of draw one of these weird graphs. Maybe I'll just draw some curvy graph. All right. So if you want, let's say here, this is 1 hour into a trip. Okay, and maybe here, this is like 5 hours of the trip. And maybe this is at, I don't know, 7 hours of the trip. Okay, so let's say we want to define the average speed between, okay, if we want to define the average speed between 1 and 7 hours, okay, what that would be equal to, we could take the position at 1 hour. Let's say at 1 hour you were, I don't know, 50 miles away from your home. Okay. But at 7 hours, you might have been, I don't know, 80 miles away from your home. Okay. Well, to find the average speed that you're going over this time frame between 1 hour and 7 hours, all that's equal to, it's equal to the slope between these points. If I were to draw on a line here, if I were to draw on a line, the slope of this black line would be equal to the average speed. So if we want to find the average speed between 1 and 7 hours, okay, we take the absolute value of the change in distance over the change in time. Well, what's my change in distance? I started at 50 and I ended at 80, these time periods. Okay. So my change in distance, the difference between these two is 30. Well, the absolute value of the difference is 30. Okay, so that'll be 30 miles. Okay. So maybe you were going, then you forgot something somewhere, so you had to backtrack a little bit, and then you kept moving forward. Okay. And your change in time, well, you're going between 1 hour and 7 hours. So the change in these two numbers would be 6 hours. Okay. So you do 30 divided by 6, which is 5, and you're only traveling at 5 miles per hour. Maybe you're not in a car, maybe you're on a bike. And maybe you're on a bike, or maybe you're walking even, for that matter. It's probably more likely you're just walking there. So that would be your average speed over these 6 hours, between 1 hour and 7 hours. But when we talk about instantaneous speed, and before we get there, sorry, this line between 2 points has a special name. That's called a secant line. And the slope of this secant line is equal to average speed, or average rate of change. Okay. Now let's compare that to instantaneous speed. Let's say you were walking, okay, you're walking over this whole time period, you're walking for 7 hours. But if someone was able to put a radar on you exactly at the 5 hour point, they could measure your speed at this exact instant in time. And this type of line has a name. It's called a tangent line. It just hits at this one point rather than over this long time period. And the slope of this would be your instantaneous speed. Okay. And this tangent line looks a tad bit steeper than this one, so you're probably going faster than 5 miles per hour because the slope's a little bit, it's more slanted, or I guess it's steeper. Okay, so that would be your instantaneous speed at that time. And that's what some of these words are. Now, we can't actually calculate this with what we know now. Okay, the calculus is actually going to help us figure out what the slope of this line is, the slope of the tangent line. And that slope has a special name, which we'll get to down the road. That's called the derivative. Now coming back to the note card here, let's go ahead and do some problems to help us understand. It says a roller coaster has its largest drop modeled by this equation. Okay. Where d of t is measured in feet and time is measured in seconds. So if we were going to plot this out on this axis, we would put the, okay, d of t, that's measured in feet, and time is measured in seconds. Now I'm not going to this side because you can't have negative time. And on a roller coaster, you're never going to go through the ground, so it's not going to be negative. So maybe this is like feet above ground. Now on some of these note cards, if it says calc next to it, that means you can use your calculator. It says, what's the average speed of the roller coaster from 2 seconds to 8 seconds? Okay, so let's go ahead and graph this. So if you get your calculator out and you go to y equals, you can plug in the equation of that function. Now, when you plug it in, it's not going to let us use t's because that's not what the calculator likes. We actually have to use x's, but we get it the same way as we're used to. We hit that x, t, theta, n button, and it will always default to x's when we're in function mode. Okay. So once you plug this in, before you hit graph, okay, just hit window for a second. Now, instead of x's, remember x's are like times, so let's just look at it to start with between 0 and 10 seconds. Okay, and we'll scale it. Each tick mark will be 1. Now we know y min's not, it shouldn't go beneath. Okay, so let's start it at 0 there. Right. But we don't know how high to make it go up. Okay, so what we can actually do, the calculator can help us with that. If we hit zoom and we go down to option 0, which says zoom fit, it'll make an appropriate graph for us. So I'm just going to go down to 0 and then I'm going to hit enter. And the calculator is going to do the work. It's not going to make me keep picking different numbers. So that's the shape of the graph between 0 and 10. Okay. So I'm just going to kind of copy that graph over here. Now we want to know what the average speed of the roller coaster is from 2 seconds to 8 seconds. All right, so if I hit the trace button on my calculator, which is right there, and I type in 2, it's going to tell me what the height of the roller coaster is. When you're 2 seconds into the journey, 2 is time. How did I get that? Let me get out of this real quick. After I hit trace, all I did was type in 2 and hit enter. And the height at that time is 274.47. So this was at 2, all right, and that's 2 comma 274.47. Now we can do the same thing at 8 seconds. So I'm still in my trace mode. If I just hit 8 and hit enter, that's going to tell me the height at 8 seconds, the height of the roller coaster. It says 20.97. That's about right there. Okay. So at 8 seconds, this point is 820.97. So I want to find the average speed of this roller coaster. Okay. So if I want to find average speed, I can use that formula above. It's absolute value of change of distance over change in time. So if I think about this, if I'm going to go starting at the bigger minus the smaller, all right? So I ended at 8 seconds, I was 20.97 feet above the ground. Minus, and when I started, I was 274.47 feet above. And that unit's going to be in feet. Okay, now what about your change in time? You ended at 8 seconds, you started at 2 seconds, or at least the part we care about. So the change there would just be 8 minus 2. And that would be measured in seconds. So my units should be feet per second when I'm done. Okay. So we can use our calculator here to help us out a little bit. Okay, I can do 20.97 minus 274.47. Now that's negative 253.5, but that's got absolute value bars. Okay, so that's going to make it positive. So 253.5. Okay, and 8 minus 2 would be 6. So if I do that in my calculator, 253.5 divided by 6 will be 42.25 feet per second. Okay. If we were to draw a secant line between these 2 points and find the slope of that line, okay, that would actually have a slope of negative 42.25 because this line's actually going down from left to right. But since we're talking about a speed, we would have to be smart enough to make it positive. That's what we would have to do. Okay, now let me show you another way how we can do this really quickly, really easily. Okay. Now, remember, these two came from y values. They came from y values from the function. And I put this function into y1 in my calculator. Okay. So, let me just kind of show you a quick way. If we think about this number right here, this was the y1 function evaluated at 8 seconds minus this number right here was the y1 function evaluated at 2 seconds. So just watch what I do here for a second. Zoom in so you can see what I'm doing. So we can do this in one step in our calculator. I can go, I need to get a fraction, so a shortcut to get a fraction, I'll hit alpha y equals, and I'll choose option 1, which says n over d. Makes it like a fraction. Okay, now I need absolute value bars. And there's a shortcut for that too. If I hit alpha, hit y equals again, but now toggle over to where under the function menu, the first option says ABS, which stands for absolute value. So I'm going to hit 1 or enter here. I'm just going to hit enter. Okay. Now I want to put those two numbers that I got before. Okay. I can take the y value at time 8. Okay. So watch what I do here. I can use another shortcut. Alpha y equals, and I'm going to keep scrolling over until I get to the y variables menu. Okay. Well, my function's in y1, option 1. So I'm going to say calculator, I want the y value at 8. I'm going to do the same thing again. The y value at 2. That's all underneath absolute values. So that number would come out to 253.5. Okay, and on the bottom, we just put 8 minus 2. And I hit enter, and what do you know? Right there, all in one step, it says 42.25, which is exactly the same answer we just got, 42.25. So that's a shortcut that you can use on your calculator. Part B, it says, what's the average speed of the roller coaster from 4 seconds to 6 seconds? So basically, same graph, we have the same function, but now I'm going to narrow it down. Instead of looking at it from 2 to 8, I want to look at it from 4 to 6. Okay. I want to look at it from 4 to 6. So I'm trying to find the slope of this secant line, but then I'm going to turn it into a positive number. Okay. So the shorthand, the average speed over the time interval 4 to 6 seconds, okay, all I have to do is I have to just say, okay, I'm going to take the absolute value of the change in distance over the absolute, or over just the change in time. Well, change in time is just going to be 6 minus 4. But the change in distance, I want to take this y value minus that y value. Well, I have it stored in y1. I have the function stored in y1. So take the y value at time 6 and subtract the y value at time 4. If we did that, it would actually give a negative number, just like we got before. Because we're taking a smaller y value minus a bigger y value. Okay, so since we're talking about speed, it's absolute value, so we just do that. And just like we did before, we can do this in one step in the calculator. Now, shortcut again. Okay, we just entered this into the calculator. There's a quick way. If I hit second, and then I hit the enter button, it's going to re-enter my last entry. Well, instead of going between 8 and 2, I just want to go between 6 and 4. So I just come back in here and toggle over and change my values. And so I'm telling, okay, calculator, take the y value at an x value of 6 minus the y value at an x value of 4. Find that, take the absolute value, and then divide by the difference of 6 and 4. I'm just going to toggle over. I'm going to hit enter, and it's going to do it for me in one step, 57.69. And the units would be the same, feet per second. So the absolute value of this slope would be 57.69. As you can see, it's a little bit steeper, okay, but it's going down. That's the average speed. Okay. Now it says estimate the instantaneous speed. So now they're talking about instantaneous speed of the roller coaster at exactly 5 seconds. Okay. So here's my graph again. I want to know at 5 seconds, what's the slope of that line? Well, we don't know how to do that yet. We need calculus for that. But if I can get really, really close on both sides of that, okay, instead of looking directly at 5, what about if I get really, really close on one side, maybe at 4.99 seconds? And on the other side, what about if I go to 5.01 seconds? The slope of this secant line is going to be very, very close to the slope of that tangent line. So if you get really close to this, the estimate of that slope would be close to the actual slope of that. Okay. So that's the best way to do it. Let me show you on the graph real quick. So here was our graph between 0 and 10 seconds of the roller coaster's height. Okay. If I change my window, okay, to 4 point, let's just go from 4 to 6. And that's the graph just between 4 and 6 instead of between 0 and 10. Looks still a little bit of curve. You see a little bit of curve to it, but it looks like it's getting more like a straight line. Okay, that's what we call local linearity. All right, if I get even closer, if I go from 4.99 to 5.01, it looks almost directly linear. Because what we're doing, if I go back to my 0 to 10, so we can see that. And if I hit trace, there's at 5 right there. Okay, so I can look really, really close to there. Okay, the y value at 4.99, let me just show you. If I type in 4.99 here, the y value is 174.1459. But if I type in 5.01, it's 172.9535. Those y values are really close together. And they're really, really close together. So the best way I can estimate the slope of the line exactly at 5 right there is to pick 2 points that are really close to 5 and find its slope by doing the same thing we did up here. Okay, so the way I can estimate the instantaneous speed is to find the average speed, maybe just like we said, from 4.99 to 5.01. So I would do, again, absolute value of change in distance over change in time. And I would say, okay, y1 at 5.01 minus y1 of 4.99 all over 5.01 minus 4.99. Quit out of here. Re-enter. I'm going to change my numbers here. 5.01 minus y1 of 4.99 over 5.01 minus 4.99. And there's the slope, 59.62, or 59.620 if I round to 3 places. Feet per second. Okay. So before I actually do some more stuff with this, 5 is a number right in the middle, between 2 and 8. Okay? So do you see how those lines are kind of different? The slope of this secant line is different than this one. And we found that the average speed was 42.25. Now 5 is also right in the middle of here, between 4 and 6. Well, when we found the average speed between 4 and 6, we found it to be 57.69 feet per second. But when we get closer and closer and closer to this middle number of 5, like if I'm going from 4.99 to 5.01, the slope of this secant line is going to be much closer to the true slope, instantaneous slope, or instantaneous speed. Okay, then we got 59.620 feet per second. So the closer we get to 5 by picking points on each side, the better our estimate becomes. Okay, that's when the average speed and the instantaneous speed get closer and closer and closer. Now, what truly is the instantaneous speed? I'll show you how you can find that real quick. I'm not going to tell you a lot about it, but if I hit second trace, and I go down to option 6, this thing that says dy over dx, okay, when it says calculate, it's kind of hard to see, calculate the derivative at a point, if I type in the number 5 and hit enter, okay, right there, next to where it says dy dx, it says negative 59.62. So the true instantaneous slope right there, or the true derivative, is negative 59.62. Negative because it's going down. Okay. So the speed there, the true speed there would be positive 59.62. Well, what did we get for an estimate? What do you know? 59.62, because we picked two values really, really close. So that's the instantaneous speed. So this was the first note card. Hopefully the video kind of solidifies your understanding a little bit. If you have any questions, just let me know. Remember that speed, big things to take away here. Speed is the absolute value of velocity. Speed's always a positive quantity. That's an important takeaway. Okay. And the other big takeaway, the closer you get to a value, so like for 5, if we're far away and we look at an average speed, it's going to be different than the instantaneous speed. But the closer we move these numbers in, like the 2 and the 8 here, the closer we move them into 5, as we get them to like 4 and 6, okay, we get a better representation of average speed close to 5. Okay, or instantaneous speed close to 5. If we get really, really close, then the slope of this secant line between these 2 points is going to be really, really close to the slope of this tangent line. And hopefully that helped you out. So thanks for watching.